All right, so there's an angle attached to that A that is going to produce that ordered pair radical 5 over 5, comma 2 radical 5 over 5. All right, so that's not going to be one of the initial ones. The initial ones are going to be more like, let's see if we can find, kind of slow down here a little bit, zoom in maybe. Oh, okay. That's not one we're going to be able to find right away. That one's not one either. Let's do this. Let's go. Put some points on here. We're used to a 30-degree angle, right? Okay, so let me ask for B instead of B prime, surtext B prime. Okay, so that is going to be one that's kind of nice. Okay, so that's a nice, concise, even though it's got fractions and radicals, it's a nice set of them. Okay, and we can, so that was attached to a 30-degree angle. There's going to be ones that are attached to 45-degree angles. There's ones that are attached to 60-degree angles, and those are the ones that we're going to mess with initially. Okay, so that's kind of where this is going to go. One of the things that they're going to ask you is, okay, if I give you this ordered pair here, and then they'll give you random ordered pairs and ask you, does it lay on the unit circle? Is it a point that belongs on the unit circle? Okay, does it satisfy the unit circle equation? So if our equation for the unit circle is this, that's an x value, that's a y value, right? So the algebraic proof to show that this is true is just to plug that stuff in. Radical 3 over 3 squared plus radical 6 over 3 squared, and we're going to ask, does that equal 1? What's radical 3 squared? 3. 3 squared would be 9, right? And this will give me 6 ninths, correct? Is that a true statement? Does 3 ninths plus 6 ninths equal 1? Yeah, okay. So yes, this does exist on the unit circle. Let's go back to this one here. Okay, think about that. If I take that number right there and square it, what do you get? 3/4. What do you get if you square that number? 1/4. If you add those together, what do they give you? 1. Does that make sense that it gave you 1 because that point is on the circle with a radius of 1? Okay. So everyone, if I did that with this here, okay, this ordered pair, I'm going to get that. And we can, you know, if you want to go like point A, so I can go like x of A, so that's taking the x value of point A and squaring it and adding to it the y of point A and square it. When I hit enter, it's going to create a number here in a number column, and it should be 1 all the time. So we get that number right there, right? We're seeing that it's being produced by what's in that yellow box. No matter where I move A, does that number ever deviate away from 1? No, that's because A is always on that circle, right? Okay. So that's one type of problem that you're going to come across. Just want to make sure that we see something like that and understand that we are working here with coordinates, okay? And we're working the coordinate plane. What is, I think, gets lost on us sometimes, and we'll see this with like a picture like this, okay? I think with this picture, it gets lost on us that we're working inside the coordinate plane. What I need you guys to understand, every single time you do a problem like this, you are working in this region. Let's go. Try and think the best way of doing this. -1, less than x, less than 1. Okay. When work with the unit circle, we are going to be in the coordinate plane, but we're always going to be zoomed in on those 4 blue boxes. Does that make sense? Okay? And that gets lost on a lot of people when they start giving us pictures that are zoomed in and don't have grid lines and are looking like this. Okay? Does that make sense?
Yeah.
Okay? So if we read this, says, suppose t is a real number. It says if t is greater than or equal to 0, we mark off a distance t along the unit circle. So what they're doing here is that they're going to allow t to be a distance of this arc. Does that make sense? Okay. So they're going to measure some distance t, and if it's positive, that they're going to move counterclockwise. Okay, which is the same movement that we moved when theta was positive in chapter 5, right? Okay. In this instance, they're talking about, instead of theta, they're talking about the arc length t. Okay, we'll talk about this here in a moment. But your initial point, your starting point, is going to be that point right there. Does that make sense? Okay. So that's my initial point. We call this here our terminal point. Just humor me real quick. Chapter 5 said that blue ray was an initial ray, right? It said that this purple one was a terminal ray, correct? Do you think there's a linkage here between initial point and terminal point? Initial ray and terminal ray?
Yep.
Yeah. Okay. And let's talk about that linkage real quick. What kind of circle are we working with here? Unit circle. So when we talk about, does anybody remember the formula for finding an arc length? Finding that red distance. If I were to walk that red distance. It incorporates theta r. Okay, so S, my right, is r theta. So that was, and that this would be if theta was in radians, correct? Okay. So that's arc length. That's the formula for arc length. Now, I don't know. Some textbooks actually use S instead of T in this situation. Not 100% sure why this textbook uses T. I've seen other textbooks use T as well. But S is the same thing as T. Does that kind of make sense here? So I can make that kind of extended equation. What circle are we in? What did you say we were in? The unit circle. So what's R? 1. Does that make sense then? Okay. Well, what was theta? Theta was that angle right there, wasn't it? Okay. So when they talk about, on the unit circle, when they talk about this distance t, you can make the connection, you can make the jump that yes, we're talking about this length t, but that is analogous, essentially, because of this relationship here, to that central angle of theta. Okay? And because of what we did in chapter 5, I think most people are going to probably be more comfortable working with the theta instead of the t. Okay? And I don't know if that's why they choose T instead of S, is because T and theta start with the same letter, right? Okay. So I don't know if there's a mnemonic link there for some reason. But I think that's an important relationship. So if we're moving clockwise, like we did in chapter 5, in this case you're going to say that T distance is negative, but then the central angle of theta would be negative as well, right? And that's comparable to what we did in chapter 5. When we move clockwise, you are going to attach with it a negative idea. That tells us the direction of movement. Okay? So counterclockwise is positive, like chapter 5. Clockwise is negative, just like chapter 5. Okay? Every time that we kind of travel this distance, and I think this is the reason that they talk about this as a arc length instead of the angle is because if I start here and I travel this distance and I stop somewhere, I stop at a point, right? If I have to rotate an angle out, then I have to be able to talk about that point being generated by a ray intersecting my circle. And then that point then is created by the intersection of a ray and a circle. And I have to talk about it that way. Does that make sense? And so it's just easier, I believe, to talk about it as a terminal point at the end of an arc than it is to be talking about as a terminal point as an intersection of an angle ray in the circle. Okay. However, when you come to rest, we get our terminal point. That's determined by that t value or the theta that we're going to deal with. And here is some stuff that we already know from chapter 5. So since circumference is equal to 2 pi r, and what circle are we in here? Unit circle. So r is 1. So the circumference of the circle is 2 pi. That means if I start at 1, 0, and I move all the way around, I've traveled a distance of 2 pi, right? Is that the same idea as when we moved around the circle completely in chapter 5? It was 2 pi, right? Okay. If I travel a quarter away around the circle, a quarter of the way around the circle, it put me at 0, 1, correct? Okay, or pi over 2. Okay. Traveling halfway around the circle puts me at pi. Okay, 3/4 of the way around the circle puts me at 3 pi over 2. And then the next picture is one complete rotation of that point t around the circumference, and it gets back to 2 pi. Okay? Get your calculators out real quick. Anyone you want, as long as it's got radian mode on it. So previously when we were looking at like S equals R theta, and that T was the same thing as S, if you remember, theta had to be in radians for that formula to work. So when we're doing what we're doing here, and we've got pi and all that kind of stuff, we'll make sure we're in our radian mode. So change to radians here. And we're going to type in those T values there. So what you guys do is we'll just start with cosine. Type in cosine of pi over 2. What do you get? 0, okay? Type in cosine of pi. -1. Type in cosine of 3 pi over 2. 0. So did you just tell me that the cosine of this terminal point that is determined by that distance is that number right there? Did you say cosine of pi over 2 is 0? Didn't you say the cosine of pi was -1? Didn't you say the cosine of 3 pi over 2 was 0? Okay. So those were all the cosines of those distances, those t values. Cosine. Type in sine of pi over 2. 1. Type in sine of pi. 0. Now just don't type anything. What do you think the sine of 3 pi over 2 is? -1. Okay. So what we find out, and hopefully through some of the discussion we have in a little bit, and maybe tomorrow, the next day, and the graphics that I show you, is that the cosine within the unit circle, the cosine of the terminal point, okay, let me rephrase, the cosine of the terminal distance, t distance, okay, or that angle associated with t, is the x value of the terminal point. The sine is then the y value of that terminal point, okay, and that is predominantly the reason why we like to use the unit circle, okay, for that feature that exists by knowing those terminal points, okay. So here's a question. This is essentially talking about what we talked about in chapter 5 with coterminal angles. Okay, if you remember coterminal angles, They were angles that shared the same terminal ray, right? Well, if I look at the idea of t equaling 3 pi, so what we're doing here is we're taking this point and we're going to rotate it around my circle a distance of 3 pi. So getting back to there would be 2 pi, right? And then it's going to come to rest right there at 3 pi. Is that okay with everybody? What's the order? And this is where I need us to remember that we're inside the coordinate plane here. What is the ordered pair of that point right there? Negative 1, 0. Okay? Type in cosine of 3 pi for me real quick.
Negative 1.
Cosine of 3 pi is negative 1. What's the sign? Before we type anything in, what is the sign of 3 pi? 0. Okay? As we work through this process, because the end goal is to be able to say, okay, what's the cosine of 12 pi over, I don't know. No, let's go 11 pi over 4, something like that. Okay? And ask you what the cosine of that is, and what the sine of that is, and what the secant of that, and the cosecant, the tangent, and the cotangent. Ask you those 6 trig functions. And the hope is that we can say, well, 11 pi over 4, that's the same thing as 3 pi over 4. And 3 pi over 4 has a terminal point at negative radical 2 over 2, comma, radical 2 over 2. So the sine is radical 2 over 2, the cosine is negative radical 2 over 2, the tangent is 1, and then the reciprocals that follow from that. Does that kind of make sense? So that's the end goal. But in order to do that, the first thing we have to get to is the point that is attached to the terminal distance. Okay? That's this t distance, or if you want to talk about it, the angle theta. Okay? What is the point, what is the terminal point that is attached to that? Because once we have the point, then the sine and the cosine come from that point. Does that make sense? Okay? So if I go negative pi, putting our point there, and now which direction am I traveling? Go this way, right? So get me right there. And what's the order pair there? Negative 1, 0. Now think about this. If I were to add 2 pi to this, what does that give me? What's negative pi plus 2 pi? Pi. What if I were to subtract the 2 pi from this one?
Negative pi. Right, no.
Still pi, right? Did they both stop at pi? Are they both, that point there and that point there, at pi? So would you guys agree that these two things are coterminal angles?
Yeah.
Okay. Or if we're talking about the arc lengths, we're talking about just the point in general, they're coterminal points. What about negative pi over 2? Where am I going to go there? I'm going to travel this direction. I'm going to stop right there. And what's the order pair with that? 0 and negative 1. So, cosine of negative pi over 2? 0. Sine of negative pi over 2? Negative 1. Is that okay?
Yep.
All right. So let's elaborate on this a little bit. We look at this picture. Okay, right now I've got 2 things operating here. I've got a circle, which is the unit circle, and I've got this line, this orange line, that is being defined by going through 0, 0, and the point radical 2 over 2, comma, radical 2 over 2. And if I think about what that line's equation is, because of, a couple different ways, looking at those 2 things, that y is equal to that x, right? So any point on that line has to have the relationship that y equals x, okay? So that's the equation for that line. Or you can think about, well, if that's 45 degrees, right, because of the pi over 4, so that angle is 45. This angle then's got to be 45 to make up the 90, right? And the line that does that in the first quadrant is the line y equals x, okay? So the question is, and how do I know, how can I verify that ordered pair? Okay, because when we start this, I should have blanked this out.
Yeah.
Maybe look at that way and ask you, okay, what are the coordinates of that point? All right, so what we have here is what we call a system. What's the word system in mathematics mean? Grouping of equations. Okay, so we have a system of, now these are non-linear equations. Okay, that's equation 1. Now that one is linear, but equation 2 is the blue circle, right? That is nonlinear. Okay, as long as one of our equations is not a line, then the system gets identified as nonlinear. Okay, the number one way for you to solve nonlinear equations is to use substitution. Okay, careful. All right.
Maybe you should stay awake.
Okay. Yeah, you fall asleep, you don't know where your arms are, don't know where your stuff is, and knock it all over the floor. Okay. So there are, if we're with nonlinear systems, and I don't know how much you guys dealt with this in Algebra 2. We didn't do a whole lot now in college algebra, but systems of nonlinear equations, if I have like two circles or two ellipses or two hyperbolas or something like that, because they have the same structure, maybe I can use elimination. You guys remember elimination?
Yeah.
With systems? But if they don't have the same structure, a circle and a line don't have the same structure, so I can't use elimination. So I have to then rely on substitution. So what I'm going to do is I'll take if y equals x, I'm going to make that substitution right there. So I get x squared plus then x squared is equal to 1, right? How many x squareds you got there? 2. Would x squared equal 1? Half? Divide by 2. So then x will equal, now I'm introducing a radical, so it's plus or minus, root 1/2. Which if I rationalize that, it becomes that. Does that make sense? Okay. Now, so that's what the x value is. It's radical 2 over 2. The y value is x. So the y value is radical 2 over 2 as well. Okay. Now, when we did that algebra, we took a square root. We introduced a negative, right? Because this line and this circle actually have 2 intersection points, right? Would you guys agree at that point is also, now it's the negative version of that, right? Does that make sense? Yes?
How did you get the radical 1/2?
Because if I've got a radical of a quotient is equal to the quotient of two radicals. So I put radical 1 over radical 2, right? Radical 1 is 1. So 1 over root 2. And then I rationalize. I multiply by radical 2 over radical 2. It's not wrong, but we're never going to, in all the things that we do, ever see root 1/2. We're going to always see root 2 over 2. They're always going to simplify it and write it that way, and it's just going to be a common structure. Okay, so hear with me here real quick. Wow. That distance right there is pi over 4, right? Pi over 4. Pi over 4. Another pi over 4. And another pi over 4, right? How many pi over 4s did I just mention? 5. Type in cosine of 5 pi over 4. Negative 0.707, right? What's negative? What's negative root 2 over 2? Same thing. Negative root 2 over 2. So, from this information, we now know what the sine and cosine of pi over 4 are, and we also know what the cosine and sine of 5 pi over 4. And we also know, I could go the other direction, type in cosine of negative 3 pi over 4. So negative 3 pi over 4 would be going that direction, right? Does that make sense? And it gives me the same terminal point, so a cosine negative 3 pi over 4 should be still the same, negative 0.707. Okay? Now, that's one approach. Okay? A second approach is, we'll just do it in this real quick. Let's put an angle of pi over 4 in here. So we're trying to figure out what that point right there is. And we know that that arc of t was equal to pi over 4. But because we're in the unit circle, we have talked that that t value, going back to s is equal to r theta, s is the same thing as t, but r is 1, so t is the same thing as s, same thing as theta. So that blue distance is the same as that angle theta right there, correct? So if that angle theta is pi over 4, what's the pi over 4 in terms of degrees? 45. If I drop down from that terminal point right there, that line right there, I get what kind of triangle? A right 45, 45, 90 triangle, right? So that triangle is a right triangle. Now, what kind of circle are we working inside of? Unicircle. So that's my hypotenuse right there, right? Now, in a 45, 45, 90, your hypotenuse is always what compared to the sides? 2n, right? So if I put these two triangles on top of each other, doesn't 2n match to my 1? So 2n would equal 1, so n would be, I'm sorry, I messed that up. It's not 2n. I'm thinking my 3069. It's n root 2. My apologies. So it's n root 2. N root 2. So if that's the case, how do I solve for n? I divide both sides by root 2, right? Divide by root 2, so then I rationalize this and I get that, right? And that's my n value. That would be that distance right there, correct? Which compares to that distance there, correct? So that distance, root 2 over 2. Is it also that distance there? Which correlates now to that distance, right? Now think about this, and this is where I think it's important for us to remember, and this is why I did it in GeoGebra, we're always inside the coordinate plane, right? So this distance here, if I want to go from 0, 0, and I travel along this blue distance here, that's terrible. Let's see. Let's try to get something that's a different color than what's up here. I want to go from that point there, and I travel this distance, which is radical 2 over 2, and then I follow it by that distance, which is radical 2 over 2. It gets me right there, correct? It gets me to that terminal point. I travel an x distance radical 2 over 2, travel a y distance radical 2 over 2. So the terminal point associated with pi over 4 using special right triangles is radical 2 over 2, comma radical 2 over 2. Does that make sense? Okay. So if we can do that with a 45-degree angle, let's do this real quick. What's another angle that we like to use? 30. Okay, so let's say that we've got a terminal point here with that distance. Okay, what is 30 in radians? Pi over 6. Okay, so let's see what is the terminal point associated with pi over 6. Well, if this is the unit circle, again, we know, you might want to have that checked out. We know that is 1. Okay, this angle here is the same as t, right? So this is 30. Right triangle, correct? In a 30, 60, 90, this is 2n. That's 30. This is n, and this is n root 3, right? Well, if I overlap these, 2n and 1 match up, right? So what's n going to be? 1/2, correct? So is that blue distance right there 1/2? Is that the y value of that point? Is this distance right here then 1/2 times radical 3? Which that blue distance is this x-coordinate of that point right there, which if I rewrite that, it's radical 3 over 2. Just real quick, just so we can make the connection real easily, take your calculator, type in sine of 30 degrees. We talked about the other example is that sine is the y value, right? So to give you back 0.5. If you type in cosine of 30 degrees, it should give you back 0.866 or something like that, which is radical 3 over 2. Does kind of make sense? Okay. Is there another angle that we like to use? 60. Okay, now we're not going to do all of this one, because if this is a 60-degree angle right there, this is 30, right? Is this still 1? So that's 2n. So isn't n still 1/2? It's just now that distance? And that distance now is radical 3 over 2. So now that point is 1/2 root 3 over 2. So if you type in cosine of 60, you get 1/2, right? Okay. Cosine of 60, and I'm thinking about this, sine and cosine are the same words, but one says co in it, right? Okay, we just said that the sine of 30 was 1/2. The cosine of 60 is 1/2, right? What do you get when you add 30 and 60? 90. And what's the word for two angles after 90? Nope. Complementary. So the idea of complementary in these words, sine and cosine, is the co that differentiates is the idea that we're talking about cosine or complementary angles. Okay. All right. So that generates this picture here. Okay. If we were to go through, use our calculator, and ask, what is the cosine of pi over 6? It's going to be the x value of that ordered pair at pi over 6. If I ask, what is the sine of pi over 3? It's going to be the y value of the ordered pair attached to pi over 3. Okay? Those are 3 points in the first quadrant that we need to come to terms with. Okay? I'm not saying memorize them. My hope is that you learn that they just came from a 30, 60, 90 triangle and a 45, 45, 90 triangle, and you don't have to memorize them, right?
Yeah.
The quadrants, okay, the pi over 2 and the 0 and the pi and 3 pi over 2 angles, those should be at this stage just knowledge. I don't think, if you don't know that, I think we're in trouble. Here's my question to you, okay, in the next couple minutes. If I took this arc right there, and I fold it on the y-axis, will it land right there? Does that make sense? Okay. Now, when I fold on the y-axis, I'm talking about a reflection, right? If you go back to geometry, throw some vocabulary out here, a reflection is a rigid motion. Okay? Or a reflection is what we call an isometry. Okay? What that means, think about something that's rigid. Something that's rigid. People that are rigid are, like, they're set in their ways, they do it their way, they're not going to change, right? Does that make sense? That's what rigid people are. When we talk about rigid in regards to geometry, a rigid motion means that distances are not going to change. They're stuck in what they are. They're not going to change. Okay? By definition, an isometry is what we call a rigid motion. Okay? It's where distance does not change. Distance is preserved. And the reason I talk about that is if I make a reflection, this point right there is going to go to like right there, isn't it? That makes sense? Okay? So, that point here is going to go right there. Okay? Now, if I reflect it on this axis, that distance right there and that distance right there cannot change. It's a rigid motion. Does that make sense? And for the same reason, that distance right there and that distance right there cannot change. Does that make sense? So what's the ordered pair for that point right there? If distances cannot change. Okay, so that point right there is the same exact ordered pair as that one, except for, because we're working in the second quadrant, aren't all ordered pairs in the second quadrant negative, comma, positive? Does that make sense? Yes. Okay, so let's think about this. Just answer this real quick. This distance right there would have been how far? That yellow distance, maybe use this blue distance. How far is that? That was pi over 3, right? How far do you think that is? Pi over 3. So pi over 3 plus pi over 3 is 2 pi over 3. Type in cosine of 2 pi over 3. Make it 1/2? Yeah. Cosine of 2 pi over 3? Yeah. Being radians. Does this stuff make sense? Yeah. So these are the building blocks of being able to quickly identify when I give you an angle like 27 pi over 4, that you can quickly identify what the sine, cosine, secant, cosecant, cotangent are for that angle measurement. Okay. We will construct the complete unit circle tomorrow. Okay. And I'll probably have something printed off for you, like a map for it, make things a little bit easier drawing it for you.